Okay, so, well, as the host, what do I say? Welcome, everyone. We're going to do some integration today. As a surprise, it's more towards the A level, and I think there are at least some people who are interested in doing that. And whilst we wait just a few moments, there's a few riddles in here, A, B, and C. See if you can guess what they are trying to say. So they're trying to say it literally. And I'm joined today by Maths Explained. So hello.
Hello.
Microphone working and all good.
That's good. How are you feeling with your first live stream?
Feeling good. Like I like to be back here. It's a good feeling. And yeah, looking forward to it. The question I have is, do people know, because I probably should have scheduled it, but do people know that it is now live? But never mind, the show will go on.
Even if people don't catch it live, they can see after the fact. They can watch the video after the fact, so...
Yeah, exactement. Exactly. Okay, so these particular... Let's just go through them, eh? These particular riddles, should we call them, are also known as dingbats. I don't know if you've ever seen them, but I've made these myself. And they're basically, they're literally what you see. So if you think about this, on the left, we've got sine over cos, which is another way of saying tan. And then on the right, if we have ln applied to e to the u, disappears and becomes u. And so what this is really saying is thank you. But in maths speak, you know, it's a little bit dorky. I put the answer down here in this little box. And this one here, I don't know if anyone got... Did you get this in the end? Maths Explained?
No, didn't. I worked out the first one. I haven't worked out the other two yet. It's either something about parallel lines or... yeah, that's all. Initially, I thought they were all related. Like, I thought it might be a sentence.
It's
Oh,
literally parallel lines. You got it.
okay.
Yeah. I was like, you know, these represent lines and they're sort of literally parallel. So it's sort of just saying what you see. And what about the last one?
Flubberdence.
Yeah, because it's
No,
so easy to get carried away with the whole word that you've got there. It was not a word you ever see normally.
is it a word?
It's not a word. No,
Oh, it's not a word. Okay.
it's a play on words.
Flubberdence.
Probably the hardest one here. I can give you a
Flu
clue.
bad.
Say again.
Flu bad.
Yeah, right. We've identified that word that's important.
Ents. Flu bad.
We're just here
Um,
entertaining ourselves on a lonely planet called the internet.
Something to do with the forbidden word, but I don't know. I'm too slow.
Well, this one actually is. I can't. You know what? I have an issue here. I need to switch screens because suddenly my input pen is only applying to my laptop screen.
Oh,
So useful.
do you have like a tablet or a
Yeah, graphics tablet.
graphics tablet, right?
Is there any setting that I don't know if you know
Is it,
about?
what brand is it?
It's just a well, it's fairly cheap, but it's lasted me a while. It's a Hoyon.
Okay. I know
Hoyon.
Wacom has settings that where you set the screen that you're writing on.
Yeah. I'm not 100% on that.
Yeah, I don't know.
Although there is a graphics pen here. edit pen menu, pen settings. Choose which hand, additional pen settings, choose handwriting to enter your text, find your pen, tips, how to change the battery, that's it, there's nothing. No, there isn't anything I can do from Windows settings. Well, I have to do a switcheroo. I don't know how to do that without disrupting everything.
Oh, you want me to move the box?
I can. Oh, I could definitely move the box. The issue is like I can't write with my pen later.
Yeah, you're going to have to fix it. Yeah.
So this never happens before. I chose the top screen because it always works on the top screen. Anyway, let's have a look at this last one. Bad is the word that you found in the middle, and if you get rid of the word bad, you have influence. So it's bad in fluence.
Bad influence.
So like it's the word bad inside the word fluence.
Oh, that's cool. I like that. Bad
Yeah,
inside.
yeah. I like these. They're kind of fun, you know. I'm trying to figure them out. Right. The only thing is, how do I switch screens without revealing my secret identity? To put it a funny way.
Oh, I'll be back in 5 minutes.
Okay. Well, we'll take a break while I do that anyway. Okay. Gosh, that's annoying. Oh gosh. How to change? Maybe. Doesn't matter if that goes away, so I can change this one first. Put it up there. Then change the display to display 1. Slightly strange thingamajig. Okay, here we go. And is it working now? Yeah, finally, here we go. Excellent. We can actually do some. We're up to business now. Let's get some of these other screens out of the way. Everyone that's just joined, just to let you know, Maths Explained has a knock at the door. So back in a few minutes. But in the meantime, I've had to change my screen because wouldn't you know it, the pen decided to only work on the opposite screen to what we have everything set up on. So back to business, and We had a few of these riddles. We didn't know if anyone would turn up, but here you are. Nice to see you, both of you. And it's sort of more geared towards A-level, we thought today. There were some people asking for some integration, some A-level geared questions, and well, in honor of a colleague of mine that passed away, we decided to do some questions on integration, well, the rest is history. We've got these lovely things here called dingbats, but I won't go through them again. You can find a ton of them on my Instagram if you're interested in them. They're quite fun. You can see the answer down here at the bottom. So I'm just going to very quickly whip out my working out, because I want that over there. It's all a bother, you see, because I started live streaming and halfway through I've had to change the screens. I had it all lovely and set up. And there's another caveat to this. We're going to start the stream today with some questions on the integration side from Maths Explained. So before we move on to do the first question, we'll still wait for a second. So how has everybody's week been with the maths? What's been bothering you? Yeah, everything's set and ready.
Back. That was about the worst possible timing.
Yeah, well, it was okay. We've got a couple of people that joined our stream. A couple of friends, should we call them?
Waha and HA, welcome.
Got Math Paper 1 mock next week. Oof. Are you nervous, or is it good fun? As I was explaining that, so you're going to start us off, aren't you?
Okay, yep,
so
sure.
Whenever you're ready, then go for it. But yeah, I was just having a chat first.
Okay, cool. Well, so you explained we're doing integration today.
Yeah, had a little explanation, and if anything, for some people that want to be doing GCSE, this could be an interesting sort of lecture style, if you will. We could explain it in such a way, perhaps, but there will be a point where it will just be interest if there are any GCSE. And some people want a flavour of A-level maths. That's still a good thing, I think.
Sure. If you haven't learned any calculus, it's probably not worth the time to. I mean, don't. Another way to say it would be, don't stress if you don't understand any of it.
I like that, because it might be a bit strange. Like, you might have a lot of questions, right? So.
Yes.
But I would say this: people that look at the maths that we do in A-level and they think, "Oh my goodness, we have open evenings where they can come along and see some of the work and the books and what we do," and a lot of people are very intimidated by it. And I always tell them, don't think about this as the kind of work that you cannot do. Think about it as the work that you'd be proud to be able to do. Because if you just take those baby steps, we'll get you there. And you will get to this level, and it will be fairly straightforward for you.
Yeah. I guess if you're watching as a GCSE student, maybe see if you can spot one thing that you don't understand, and see if you can understand that one thing. So if you don't know what this symbol means, this squiggly S, maybe that's the thing you pick out and say, oh, I want to understand what that means. Or just pick out a few things, and maybe that's a constructive thing you could do if you're watching. So yeah, I thought I didn't pick too challenging problems for this session. Mine are pretty basic, sort of standard integration problems. And then I think maybe you're doing some slightly harder stuff.
Slightly harder, yeah. I just thought a big range would be more interesting, but
Yeah.
it's actually quite good because Waha is actually just finished self-studying year two, so
Okay. So, uh, well, this should be pretty uh, standard for him, but maybe still some good revision. So, the main thing I'm going to be focusing on is the power rule, which says the integral of x to the n with respect to x is equal to x to the power of n plus 1 over n plus 1 plus c. This is, of course, when n is not equal to -1. When it is equal to -1, then you need the log, but I won't be using that. So this, you learn about this after you learn about integration, and this is basically a shortcut. All of the integration rules are shortcuts, so you don't have to do it from first principles every time. But here we're going to apply this power rule to each term in this expression. So it says, this question says, find a fully simplified expression for the integral of f of x dx. Here's the function. So we just apply the power rule to each term. So the integral of f of x is, if we look at 6x, we add 1 to the power, that's going to be x squared, and then we divide by 2. So 6 divided by 2 is 3. So that's our first term. And then we have 9x. The square root of x we can write as x to the power half. So half plus 1 is 3 on 2. So we could do this in 2 steps, just to be really clear. 9x to the power of 3 on 2. And then we divide by 3 on 2, or multiply by 2 on 3. And then 4 on x squared, we can think of that as x to the power of -2. So this will be -4 multiplied by -2 plus 1 is -1. So the whole thing is just being multiplied by -1. In other words, we're going to have a +4 and then x to the -1. And don't ever forget to plus the c on the end for an indefinite integral. And then just simplify, neaten things up. So, we've got a 2 there. We divide by 2, divide by 3, multiply by 2. So 6x to the 3 on 2 plus 4 on x plus c. And it's up to you if you write it as x to the power -1 or 4 over x. It's really just a matter of taste, I guess. So there we go. I guess we'll do one more of these.
yeah, this we'll probably go back a second and talk about more in detail about this just quickly. You know, the 4 over x squared. Could you go through to break that down one bit at a time? Because I feel like that's a really important skill to turn this fraction into index form.
Yeah, I guess I went over that a bit too quickly. So this was 4x. So 4 on x squared, you can write it as 4 to the power of -2. The negative exponent standing for 1 over that thing. So then we're adding 1 to -2. So -2, well, let's do the integral of this. -4. Is this on the screen, by the way?
Yeah, I've moved it across because it feels like it's what I choose. I've looked at the live stream and I'm going to move it for you as you need.
Okay. Yeah, so then we add 1 to -2, so that becomes -1. I guess you could look at that first, and then you need to divide by -1. That's just the same thing as multiplying by -1, and so then the -4 becomes +4. So I guess the main step there is to recognize that, 4 over x squared you can write as 4x to the power of -2.
For sure. Like, even break it down to be 4 multiplied by 1 over x squared, and then go from there. Even I don't know. That's the way I see it. That's pretty brilliant skill to be aware of, I think. Oh, and another. Well, let's see if it comes up first. Anyway, should we get on with the next question?
Okay. Yeah, so I'm just going to do a couple of these with the power rule, just to get the hang of this. Make sure we remember how to do it. So the integral of y dx. Here I have y. Again, I'm just going to apply the power rule to each term. So add 1 to the power. That becomes 3. Divide by 3, so I'll just be left with x cubed. Then x, square root of x is x to the power of a half. So what you could do, I guess, is rewrite this function. If you have any square roots or fractions, you can rewrite it such that you have the powers there. So then this 1 over x squared you can write as x to the power of -2. And then maybe it's easier to see how to apply the power rule. So here I have 6x to the half. I need to add 1 to that half. That's 3 on 2. So I could write that first, if you like, to reduce that working memory load. Then divide by 3 on 2, or in other words, multiply by 2 on 3. And I still have that coefficient. So if I well, yeah, let's leave that for now, and we can maybe take 2 steps. Then -2 plus 1 is -1, and if we had a negative, that becomes a positive if we divide by -1. So that's x to the -1, and the 4 becomes plus 4x, and also never forget to add the constant. So then we just need to neaten things up. 6 divided by 3 is 2, times 2 is 4. And then the rest is as it was written in the first line, I guess. You can also write 3 on 2 as the square root of x cubed if you like, but you don't have to. So yeah, that was just a couple of practice problems using the power rule. I guess this is good if you're just learning about integration, or maybe you're revising. Maybe this is a good,
Warmer up.
warm up.
Can I ask you a question, Matt explained?
Or
Like, why? What's the rule with numbers? Why? How come a 4 turned to a 4x?
Well, I guess you can think of it as x to the 0 there, sitting there in front of the 4, and then you add 1 to it, becomes an x.
That's
but if you're asking,
that's cool. I was just thinking, like, it's one of those things that people accept and say, oh, what happens to it's like differentiation? If there's a number, it just goes. It's like, well, have you ever questioned that? So that the rule does apply quite consistently, doesn't it?
Yes. So should I continue?
Yeah, let's do question number 3.
Okay, I was going to jump to this one, but
yeah, whatever question it is that you've got lined up next, I don't mind.
Okay, alrighty. Yeah, so now we have those warm-up problems under the belt. We can attempt maybe more of a problem-solving problem. This is 10 marks.
Jeez.
Probably no longer 10 marks under the current specification, but but this was the older specification.
Well, can I give a little bit of background? Can I just ask which
What?
paper did this come from? Was it which letter of the alphabet?
This was S. I don't really know what
Oh,
that means.
okay. So S is about 4 times harder than the usual paper. So this type of question for its level is not going to help you with part A, B, C. It's just like 10 marks, do it. So that's really what it's about. It's like four
Right.
times harder than it should be.
Okay. Yeah, but still, I think compared to the newer exams, I think uh, you can tell the newer exams are a step up
Yeah.
in um maybe Waha has some thoughts. I'm not sure. Okay, so it says the diagram above shows a part of the curve C with equation y equals 1 plus 2x take x squared. The curve crosses the y-axis at A. The straight line L is normal to C at A. The point B is a point of intersection between C and A. Find the exact area of the finite region bounded by C and L. So we have this quadratic and a line, and we're looking for the shaded region. So one of the great things about integration is that it gives you the area under a curve. Hopefully you've learnt about this already. We're not going to be proving why that's the case. That's a whole separate lesson. But it is the case that when you take the integral of a function, it gives you the area under that function. So here, to find the shaded area, what we can do is we can find the area under the quadratic from 0 to wherever the line and the quadratic intersect, and then subtract the area under the line. What makes this a little bit complicated is the fact that the line and the quadratic intersect below the x-axis. Well, let me draw just a slightly bigger picture. If you have some function and you integrate, let's say this point over here was 2. If you integrate from 0 to 2, you'll find that entire area. This area will be negative. So if, for example, you're asked to find the area, the exact area, you need to, well, usually the approach is to find this positive area and this negative area and then add them such that you're not cancelling each other out. So you basically want to multiply the negative area or change the negative area to a positive area if you're looking for area. And so here we could integrate from 0 to this intersection point B, and we would get this little area in here. And then we could integrate under the line also. And it's a little bit hard with the precision of this pen, but basically if you did that, you would find that the areas, if you subtract those areas, you'll get the area. Another way to do it is to translate the entire graph up such that the line and the quadratic intersect on the x-axis. So what we want to do is to find this point of intersection and see how far we want to translate the whole graph up. So that's the first thing I'm going to do. So what I was saying there is there's a couple ways to solve this, and you kind of have to decide which way you solve it before you begin, which is a little bit tricky, but yeah. So to find B, I want the equation of L, which involves finding the gradient. So because we're told it's the normal, that means I can find the derivative of the function at A first. So that's where I'm going to start. So for dy on dx, I'm going to find the derivative of y. So well, we're no longer doing integration, we're doing differentiation, but we're kind of using the same rule here. We take the exponent and now we subtract 1 and we multiply by that exponent. So if we have negative x squared, then this becomes negative 2x. And then 2x becomes plus 2. Okay. So that's the derivative. That means the gradient of the tangent at A is negative 2. So the gradient of the normal, in other words, the gradient of L, will be negative a half. Why have I got... Shouldn't the gradient of the tangent be positive?
Looks like it, but when you find a gradient, you've got to put in a point, right? So
yeah. So sorry.
It's easy because that's actually a really good learning point, right? It looks like a linear equation, but you've got to put it in.
That's why I got confused. Yeah, at x equals 0, we need to find dy and dx equals 2. Apologies. So this is the general derivative, and then of course we need to find what the gradient is at A. So we need to plug in x equals 0, and then we get that slope, which is 2 when x equals 0. So then we get the gradient of L, which is negative a half. And then we also have a point on that line, so we can solve for the equation. This is going to be, well, let's write out the formula. And then the point, let's use point 0, 1. So when x equals 0, y equals 1. Then we get y take 1 equals negative a half x, because x1 is 0. And so the equation of the line is negative a half x plus 1. And what next? So we have the equation of the line. What was the point of that? That was to find the point B. So how do we now find the point B with this equation? We find where it intersects with the quadratic. And I believe probably the simplest way to do that is to plug this in to our original function. So if we let y equal y, we will get, so let me write, this is finding b. We'll let a half x plus 1 equal all of this quadratic, 1 plus 2x take x squared. And can you still see what I'm writing on the screen?
Yeah, I'm trying to keep up. It's best to keep to the left so you can still see the question, but I've scrolled down a bit, so I feel like you can.
Okay. Yeah, I don't know if it's possible to zoom in or out. But
I tried, yeah. I'll try again.
Okay.
There you go. Zoom.
All right.
It might be harder to write now, but you have to be a bit smaller. Yeah.
Yeah, it doesn't affect my screen, just yours.
Yeah, but I'm the one streaming, so I guess that's all that matters.
Yeah. Okay. All right. So we're solving for x. This becomes x squared. Take 5 on 2x equals 0, which makes sense because we have a point at x equals 0, so that we wouldn't have a constant there. And then we get x equal to 5 on 2 also. So that point B is at x equals 5 on 2. Then we could also find the y coordinate. This implies y equals if we plug 5 on 2 in to the straight line equation, this becomes negative 5 on 4 plus 1, negative a quarter. And so b is equal to 5 on 2, negative a quarter. Okay, all of that was to say I want to translate this entire graph up by a quarter. So I want to move the quadratic up by a quarter. We actually don't need to move the line, or do we? Yeah, the line won't matter because we just need to find that area. So to translate the quadratic up by a quarter, we add a quarter to it. So then we could say to translate y up by 1/4. I don't exactly know the best way to say this, but there you go. So let's say we translate y to y1, which equals negative x squared plus 2x plus 5 on 4. Okay, so now we want to find the area under y1. So we integrate this from 0 to 5 on 2, and then we should be good to go. So we want the integral of y1 from 0 to 5 on 2.
That's really clever. I just want to say I didn't think doing it that way, but it's really made it easier if you can use that little trick.
Yeah, it's a good method. It's kind of a stopgap in a way before you learn, fast, more efficient methods. I don't want to say this is a bad method or like you shouldn't bother learning it, but because it's great. It's very flexible also, but there are also faster ways to do it. But also they don't make as much intuitive sense either. So yeah, I'm not sure.
As long as you don't get too lost in the whole geometry of it.
Yeah.
Sure.
So we're integrating this y1 with respect to x. So here we're using the power rule, as we were doing before. So this is going to be negative x cubed on 3. This will be divided by 2, so it'll just be x squared. Made a little squiggle there. And then 5 on 4 becomes 5 on 4x. And this is from 0 to 5 on 2. Okay. So far, so good, I think. Okay, so now, well, we only really need to worry about this 5 on 2 because if we plug in 0 here, it will all disappear. So then this becomes what we get when we plug in 5 on 2. So 5 on 2 cubed would be 125 on 8 times a third plus 25 on 4 plus 25 on 8. Okay. Then we need to simplify this. I'm probably just do this with the calculator. Well, yeah, all A-level exams are calculator exams, so you could just plug this straight into your calculator. No need to simplify by hand, but this does simplify to 25 on 6.
Yes, I got the same. Yep.
that's the area under the quadratic. And now we need to subtract the area of this little triangle here. Which has a height of, and what did we find for the line? It intersects at 1, so it has a height of 1. And yeah, actually we could translate the line up also, right? So if you imagine this quadratic is now like this, if we translate the line, that looks really bad.
That's roughly that. You can use the line function. I don't know why we're not doing lines anymore.
Then the shaded region is all above the x-axis, and this triangle now becomes from 0 to 5 on 2.
Yeah.
So, actually, let me draw that a little bit neater.
We used to be so professional, man.
Translated the quadratic up.
Oh, that's looking good.
And then we also translated the line up. That's not quite right. Something like that. So now this point here is 5 on 2, where they both cut the x-axis. And the shaded region will now be the area under the quadratic from 0 to 5 on 2, which is what we just found. Subtract this triangle from 0 to 5 on 2. That would be the length, and the height would be actually the height is changed also.
Yes.
The height now goes from now goes up to 5 on 4. Okay. So we need to subtract the area of this triangle, then we should be done. Okie doke, so the area of the triangle, I jumped down a little bit, yeah. Area of the triangle is the height times the base divided by 2. So all of this is 25 on 4 times 4, 16. Okay, so the total shaded area, or the exact area of the finite region bounded by C and L, let's write that down here. Let's just write shaded area. Shaded area will be the area under the quadratic, subtract the area under the triangle, 16. And again, just plug it into your calculator. It's really, I don't see any reason to mess around with fractions here. I mean, if you want to have some fun, you can, but yeah. What is this? What's the common factor? 6 and 16. 6 goes into 48. How many times? 8 times. So yeah, 16 goes into 48 3 times. Yes, that's going to be 125 and 48. But yeah, just plug this straight in. Okay, so final answer there for the area bounded by C and L is 125 and 48. Quite a lot of work involved. And as I said at the beginning, you kind of you need to decide your strategy, which is tricky, I think. Like having to see the strategy before you begin. I guess what you could do is you could take the integral and yeah, well, you do kind of need to know the approach you're going to take before you begin. So the other method is to simply is to simply, well, one other method is to take the integral of y, subtract L, which would also give you that shaded area. But yeah, either method is fine.
Good question. I like it. And I learned something new there. A new
Cool.
perspective.
All right.
As long as you're not feeling overworked. You got another one?
Yep. Yep. This is my last one, and then you take over.
Yeah. We'll clear the boards and then do a few harder ones from year 2.
Okie dokie. All right, another area. I think this one will be a little bit easier because there's no translating, there's no intersection between, thank you, Waha. There's no intersection point below the x-axis, which is sometimes tricky. All we really need to do here is to find the area from 0 to A and then from A to B and add those together. So I guess the first point is to say what A and B are. Now they've given us this nice factorized function which tells you the roots. So A must be 1 and B must be 3. Just read out from the, when x is 0, you can see what they will be. So, sorry, when y is 0. When y is 0. So, well, I should read through the question. It says the figure above shows part of the curve with equation y equals 2x times x take 1 times x take 3. The curve meets the x-axis at the origin and at the points A and B. Determine the exact area of the finite region bounded by the curve and the x-axis shown shaded in the figure above. Okie doke. So as we said, the integral, it gives you the area under the curve. So we want the integral of y. So let's just find the indefinite integral first. And actually, I might write this. Is there a way to move things around? I always forget.
The picture?
The writing.
I don't think so.
Yeah, we didn't find a way to do that, did we? Okay. So let's rewrite y. I'm just going to expand it out. I find it easier because then we can just apply, the rule to each term. So if we expand this out, we get 2x times x squared take 4x plus 3. And then multiply everything by 2x. Now let me just get rid of this. Multiply everything by 2x, we get 2x cubed take 8x squared plus 6x. And so now we want the integral of y in terms of x. Applying, it's not called the power rule when you take the derivative, is it?
I don't use the power rule, but by definition, so I'm not sure. I just remember what we're doing to the and why, but
I don't think it's called the power rule, but anyways, we take 1 from the exponent, multiply. Add 1, divide. I'm thinking taking the derivative, we're integrating now. Add 1 to divide, so this is 2 divided by 4, a half x to the power 4. So we are using the power rule. Yeah, I got confused because in the last question we took the derivative, so we found the derivative.
You never know when you have to take the derivative, sir.
Yeah, exactly. Okay, so we are using the power rule. Apologies for the confusion. This is going to be 3x squared plus c. Okay. Okay, so now, well, let's look at this first area. So let's do the integral of y from 0 to 1. So this is going to be the indefinite integral from 0 to 1. Then we just plug 1 in. So it's a half take 8 on 3 plus 3. Just plugging 1 in for x for each term. And then simplifying, we do need the exact area, so I guess we do need the to do a bit of work with fractions here. We could write this as 3 on 6 take 16 on 6 plus 18 on 6, which evaluates to 5 on 6. So that's the area from 0 to 1. Then from 1 to 3. Again, well, we could kind of plug it in straight away. So, oh, what happened there?
Maybe the undo button is a shortcut, I don't know.
Okay. So plug in 3 to our integral. So 3 to the 4 is 81.
Yeah.
On to 27 divided by 3 will just be 9, so this becomes 72. Then 3 squared is 9 times 3 is plus 27. And, well, here actually we're doing something we haven't... I actually didn't really talk about this in much detail because each time it's been 0, but when we are finding the area between 2 points, we subtract. And that's the fundamental theorem of calculus. I probably should have talked about that in more detail. I was just kind of going over it as a process rather than explaining myself. But we subtract the integral at 3 and then at 1, and that gives you that area. So at 1 it's going to be a half take 8 on 3 plus 3. And then when we subtract, we'll get that area from 1 to 3. Well, this is 40.5, take 72 plus 27. You know what? I would just plug that straight into a calculator. Why waste time doing mental arithmetic in an A-level exam? I mean, there are times to practice mental arithmetic, but, you know, there are definitely times not to. We just evaluated this thing. That was 5 on 6. So, whatever this is, put that into your calculator, subtract 5 on 6, and you should get negative 16 on 3. Now, it is a negative area, as expected, because it's below the x-axis. So basically that area is 16 on 3. And then to find the total area, we add 16 on 3 to 5 on 6. So you kind of just ignore the sign because we think of this as an area, not as a, not as a area in relation to a function, just as an area on its own. So the shaded area is going to be 6 on 3 plus 5 on 6. Which is 32 on 6 plus 5 on 6, which is 37 on 6, and that should be your final answer for this question.
Yippee!
Yeah.
To come back to your point on mental arithmetic, it's the equivalent of doing cardio at the gym. I don't think anyone enjoys it. But it's good for you, right?
Yeah, I should do it more often. And actually I found oh no, HA says I'm indescribably baffled. That's a risk you take when you watch or when you try to learn a subject you haven't learned anything about. It is risky, and it can be demotivating, unfortunately, if it makes you feel a certain way. But yeah, as T Formula says, I think hopefully it's something you can look forward to and say, I will understand this one day. And then that will be a really good thing. And this early exposure, it can be scary, but it can also be beneficial in some ways. Kind of subconsciously, perhaps.
Aye. We didn't get onto some of the tricks. I'm just going to clear everything so I can add the new stuff. The question is, what do I clear? Can I clear the whole thing? Or
Yeah, just get rid of it.
if I clear chat?
It's captured in video.
I didn't know we had cleared. What was clear chat though? Because we didn't have a chat, did we? I'm going to clear page drawings. Clear page images. Okay, we'll just do that. All your lovely work gone. Look at this beauty. I'll have to get rid of it though. Okay, let's set up for the next. We have files.
Well, says the fact you are even watching right now is amazing. I agree.
Actually, that might be rather important to affirm because this is probably going to disappear if I don't confirm its attendance. So I'll just wait for that to upload. Question number 3. You can tell my system here, right? Question 5. Question 4. Where is it? There we go. Ah, it's still here, but it's not.
Oh yeah, mental arithmetic. I was going to say, you know, I've been looking for an app for ages that would just give me quick problems, like quick mental arithmetic problems. So I could practice, you know, 5-10 minutes a day. And you'd be surprised, there's really nothing for free out there. There's like nothing, you know, there's a lot of paid stuff. Like there's one called Elevate. You pay a monthly subscription to do some crappy little quizzes. But I did find one single app called 7 Minute, what is it called? 7 Minute Math Genius. 7 Minute Math Genius. And it gives you problems, I think like, it gives you a minute of a set of problems like on subtraction, multiplication, division, exponentiation, and whatever else I didn't say, like just the basic operations. And it just like goes quickly through problems so you can practice your mental arithmetic. And that's all I wanted, and I finally found this app. So yeah, that's a good way to practice mental arithmetic if you want.
Awesome.
I'm not promoting the app in any way. I'm not related to it. It's just a free one.
Just
absolutely free.
Out there.
Yeah, no purchase is required, so I liked it.
Such a rare thing. Okay, let's get on with the next question. We're moving now to sort of year 2, and year 2 comes with it even more difficulties. So if you was concerned about the previous stuff, then there's a little bit more to be concerned about here. But we're going to start with somewhat of a trick, because a lot of the papers would maybe trick you into trying to integrate ln x. And what do you know about integrating ln x? You know that you can't do it, right? You said to stay away from it, but actually there's a trick to doing it. So we're going to use that trick now, and I think it's worthwhile to see it. Instead of ln x, we can use a special method called integration by parts, and we can rewrite ln x. If you looked at my recent Instagram post, did I put it on YouTube as well? I talked about how in mathematics we're always using equivalences to make our life easier. So I used an example of we use partial fractions to integrate things a bit better, or we could use the Taylor series to rewrite a function into a form which allows us to evaluate the limits of the function better than it was previously. And here's another example of such a thing. If we get creative and say, well, this is simply 1 times ln x, and we can treat this as two functions. Although I don't suppose people straight away think of a number as a function. At the very least, you might think 2x is the simplest function out there, but technically we could have y equals 4, and it is it's a number, but it's also a line where the coordinates all have a y value of 4. So it's still technically a function. And we remember our integration by parts. We select one of these that we're going to integrate and one that we're going to differentiate. We've already discussed previously that we can't integrate ln x. So we're going to be differentiating ln x. And we're going to be integrating the 1 there. So how are we going to be looking at this? Well, we can write down in terms of the formula. So probably good to remind ourselves of what we have here. We have u dv dx, and this is the format that we find our question in. If you have this format, we can write in a different way, which allows us to better tackle the question. Now, if you looking at this without any understanding of A-level, yeah, definitely this is where it starts to get a bit spooky. Lots of symbols going on. But again, if you have this format, you can use this. So we have to decide what u is. And it's always about having sort of derivatives, isn't it? And what dv by dx is. If you have a derivative here, that means you're going to integrate it to find v. If you have the u here, we're going to differentiate u with respect to x to find the derivative of u. So u in this case is the thing that we're going to differentiate. So we're going to have that as ln x. And when you differentiate ln x, probably you're thinking about what that is. English. yeah, definitely. This is all like a different language, HA. So you're sort of reading it, and once you get used to the language, you speak it, right? So then things become more comfortable. Someone's trying to tell you something fairly basic here, but if we don't know what the symbols mean, it's harder. But the standard result for differentiation, if I'm not mistaken, is 1 over x. And then we have the integral. We're going to basically integrate the 1, which is going to turn to x, because any number we're going to add the x to it. So we talked about that earlier. I won't go into detail as to why. Now we have the 4 elements in this table. I use this method a lot. I call it the table method. It in fact applies to every calculus method. Product rule is beautiful, really, because it's literally, well, it's very visual. I think I might make a video on it. It's just this one-stop layout that helps you understand. Let's go and change the color here. I'm just remembering how to do it. How we're going to do it? Well, it's u times v, so you can see it very visually. It's these two multiplied, and then v times du dx, which is just the bottom two. So it makes this sort of a shape like this. And you can learn these methods with shapes if you wish. It would be interesting if I made the video, see what you think about it. Hopefully it won't come too late for people. I should have it out by the time you come around to your exams anyway. So yeah, put it into the equation here so we can see. There's a couple of things we're looking at here. Because we've got definite integration, the limits are here, then we can think about putting it into a special formula where we have uv and we get the limits in at this point, and then the limits apply again to the result that we have at the end, which is, in my opinion, an extra layer that's unnecessary. So, it's gone funny color. What we're going to do instead is just integrate it using the rule, and once we've found the result, we're just going to plug in the numbers at the end. Let's clear a bit of space here and carry on from the right hand side. So once we shove these in, we have got x ln x to those two down the corner there, and we're going to subtract the integral of these two. So basically x times 1 over x is just going to be 1. Okay, very nice that it happens that way. Interestingly, integration by parts, remember it's like 2 parts involved, yeah? So this goes straight in, but then we need to perform a further integration. So we have x ln x, and then we're going to integrate 1 with respect to x, which is going to give us x. Now, I should do plus c, right? As every good calculus student realizes, but because I know I'm carrying on for definite integration, I also realize I don't really need it. And so that's going to go into my box. Now, we didn't really discuss either what this square box means. I'm assuming if you've got this far and you've self-taught yourself, you're kind of pretty aware of things. But just in case we didn't realize, this square box with the 2 limits here actually means something. It's like a communication. It means put e in and then subtract the result of putting 1 in. So automatically I'm sort of setting up brackets here. So replacing the x with the e, and then I'm going to put, oh, that's really good, because that's a 1 that goes in, and then ln of 1 is a very special result, which means it just disappears. And so I've got these 2 brackets, the first where e goes in, the second where 1 goes in. We just sort of clear that up. You've got ln e, which sort of disappears because ln is the log of e, and we know that any log with a base of a applied to a is going to give us 1, even if it's e, which is just a special number. So that's going to become e take away e on the right hand side, and ln of 1 is just going to become 0. It's a good result, and the negative outside the bracket is going to apply to this and turn that to a plus 1. So overall 1. That's the result for what we're looking for, putting e and 1 in. But I would say let's just take one last look at the most important result in my mind here. It's something that is not entirely in the specification, yet they sort of sneak it in there every now and again. So just be aware of it, that although it seems like there's no standard result for this, you can actually derive it using the integration by parts. So the integral of ln x is x ln x subtract x, and yes, the cheeky plus c will be at the end. Okay, that's that cool question.
It's been a while since I've seen that kind of from first, not really from first principles, but proved in that way.
You mean the integration by parts or the ln x?
Yeah, integrating log x. Well, once you see it once, you just use that rule that it equals x log x, take x.
Yeah, you can definitely remember that. That's interesting. You say x log x.
Oh, it is a log, right?
It is a log, yeah, and I think that's worth writing. Log E is ln. Now my question to you, sir, is do you say ln or do you say lon? There's two schools of thought. I don't think anyone is right or wrong, but like I've met some people that say ln and some people say lon. What were you taught? Huh?
I just say log.
You say log. Okay. Because it's ln, right? So I don't know. There's a couple of schools of thought on it.
Okay. Yeah.
Oh, and while we're at it, another school of thought, when you study maths at degree level, they don't actually write learn. They more write an extended H because it's like it's together and it's just quicker to write rather than all this separate stuff. Ah, we've got lun. Yeah, I would say lun. Okay, so that's why you follow our channel. That's because there's something deep down that we have an affinity. You see, this idea that some people say learn, some people say lon. I don't even know how to separate the people who do and who don't. All right, so let's have a look at this question. The next one, question 7. I want to check that this is actually seeable. If it's possible, if it's not too small. What do you think on your screen? Is okay?
Yeah.
Yeah, cool. All right, so let's talk about this one then. So looking at it straight away, what do you notice? You notice, okay, well it tells you parametric equations. We have x is defined in terms of t and y is defined in terms of t as well. It's this sort of independent. So already you must be thinking, okay, what are my methodologies? There are certain forms. But the first question is actually really fun. The first question is find coordinates. So it's really a play on the parametric equation idea. We get our x coordinate from the x equation. We get our y coordinate from the y equation. So whenever we want to find one, we go to the correct one. Let's look at finding one of them, right? So we want to find the coordinates p, q, r, and t. And I suppose a good place to start would be p and q. I used to work at b and q, so saying p and q is a bit strange to me. And they lie on the x-axis, right? So that's when y equals 0. So we take our second equation and we set y equal to 0 as such. And in this case, we have two solutions. Now, it's very tempting to divide both sides by t, but actually, like, you're going to miss one of the solutions because you're asking what values of t are going to give you a 0 result on the left, and it's valid that this t on the outside here, if it was 0, it's a solution. And then we've got a repeated value of 4 inside the bracket, you know, because 4 take away 4 is 0, therefore the whole thing's 0. And that's really cool. We've got the t that is involved with a y coordinate of 0. Now to get the actual coordinate, we can use that t value in the x part of the equation. So it says x here is equal to t squared minus 9. So for every value of t, there is an x and a y. So we just use the equivalent value. I mean, how can we write this? We could write it in the same sort of format, so they're sort of together. We could say that when t equals 0, we get, on the right-hand side there, negative 9. The negative is on the line. Let's make that clearer. And then when t equals 4, we've got 16 take 9, which is going to be 7. And so we've got some coordinates now. We could write them out, but we could just sort of, maybe we could do them later. Well, let's do them now. Why not? So what we're inferring here is that we've got a value of x at negative 9. So that must be p. So p is equal to negative 9, 0. And then q, being a positive value of x, must be the one on the right. So q is equal to 7 and 0. So they definitely have zeros. Okay, so the next one is, what can we tell? R, can't we? Because R is on this axis. So when we're thinking about the axis there, this is when x equals 0. So when x equals 0, we can use the equation on the right here and set it equal to 0. I don't know, maybe I should put it, I'll tell you what, I'll rub that out, and that's easier because I really have space and I don't want to run out of space. So when that is 0, we can move the 9 over, as you can see, and we have that t is going to be equal to either positive 3 or negative 3. Okay, so positive or negative, oh, it didn't write for a second there. There you go. Positive or negative 3. We'll do the same thing. If we put those values of t into the y, we can find the corresponding y coordinates, right? So when we have 3 into the y up here, that's going to be 3, 1, so we're going to have 3. And then, okay, this might look like more of a calculated job. We've got negative 3 because that's going to come 7 squared 49 multiplied by minus 3, so we get negative 147. So that's 3 less than 150. So we've got a couple of coordinates now. Let's write them here. Have we got a couple, or we just have one? Actually, we just have one. So let's do that. Because what it says in the question here is that t is not shown on the figure, right? So it's actually nothing to do with s. That's what I was just thinking. Maybe that's what we're looking for. But I think this curve sort of goes inwards. It takes a long time, but it sort of goes inwards, and eventually it gets to cross the y-axis down the bottom. There's such weird graphs, these parametrics. And so I think that's the point that we're looking at. So firstly, we definitely know r is going to be the one that's actually reasonable, which is going to be the 3, 3. But not 3, 3, but in terms of coordinates, it was when x was 0 and y was 3. And then the final one, t, must be the one that's not on the diagram. That's again when we have an x value of 0 and a y coordinate of 147. Okay, so that's the fun of it. And by doing this question, the first part at least is actually really cool. You see how parametric equations work. You pick the equation that you're interested in for the coordinate that you're focused on. So to do the next set, I think I'll get rid of everything that is not useful. Do we wish there was a better way? Yes, a quicker way. We didn't actually find a way of moving text, right? That's what we confirmed earlier. So, question being, is it possible to select? Probably not. Well, I can work around it. Time to change color. When difficulty arises, adapt. Now, for part B, we're going to go in a blue pen. Why not? So part B says, show that the coordinates of S are as such. Okay, not very nice fractions, but we're just going to boldly go on and think about what it means. What is S? S, by the looks of it, and I think I can, is it here? There we go. S is something like this, right? If that's shown up on the feed, then that's really cool. S is what we call a stationary point. It means the gradient is 0. It's going nowhere. So that's what we first think about when we think about this, is that's what we're looking for. But the question is, how do we find the gradient of a parametric curve, right? Because it's not in a nice format. There are two ways of looking at it. The first one is we could think, let's find the Cartesian equation by doing some substitution and then only having y and x. I promise that is going to produce a hideous graph, a hideous function, and actually even to get there would be pretty difficult most of the time. So that's actually probably the second to using some special technique. Let's focus on change of the rates of change and something to do with a little trick that we're not actually supposed to do, but hey, we can change the derivative form that we have based on what we are given in the question. So if we're given equations in x, which is t squared minus 9, and we're given an equation for y, which if we expand the brackets for 16 negative 2t squared multiplied by 3, bump that up, you'd have to double check this. I think it's, call it a magic trick. I think it's this. It rings a bell. But if we expand the bracket, we get this. So we're looking at what we have and what we have up here. To understand what we're looking for, we need to understand the derivative, right? So the derivative is differentiate y with respect to x. In other words, we've got a y as the name of the equation, perhaps, if you will, or the dependent variable, and then something to do with x on the right-hand side, right? I'll just make this up. Something like that. And what we have instead is sometimes an x on the left with some t's, and we've got a y on the left with some other t's, right? So we have to think about what we have. And maybe I'll leave that up there while I think about this. If I differentiate this one, it would be differentiate x with respect to t. So technically, I have dx by dt. If I differentiate this one with respect to t, I've got 3t squared. Remembering the rule actually is different from what we've been doing already. Remember differentiation, we multiply down the front with the current index and then take away one from that index. So negative 16 t plus 16. So we have this here. And these would be the things that we've got to work with. How could we write dy by dx in terms of what we have? Interestingly, if we want dy on the top, we could start with dy over dt. And if we multiply this by a fraction that allows us to cancel out what we don't want, which is the dt, it would look something like this, like dt over dx. Because this particular fraction that I've set up, the dt's will cancel and we'll be left with dy by dx. So technically this is an equivalent thing. And thankfully we do have dy by dt. We don't have dt by dx, but you can see that we have dx by dt. It's like the inverse, right? The reciprocal. So in sort of equivalent terms, we do have that as long as we do this. We've got 3t squared subtract 16t plus 16 multiplied by 1 over the result that we have over there. To cut a long story short, I might be going into a lot of detail for someone that's already studied this, but I guess it's thorough. Like some people will just learn it, right? Maybe they don't know why they're doing it. Definitely me in some places when I was learning maths. We have an expression now. Okay, so dy by dx is equal to the 3t squared subtract 16t plus 16 all over, straight enough, 2t. Oh, brilliant. That seems like it's the hard bit out of the way, right? That seems like, oh, job done, we've done it all, and that's great. But actually, how do you put values into this, right? We're thinking about the values that would be interesting to us. We've got a couple here. So we want to find when this is equal to 0. And that's pretty difficult. We set it equal to 0 because the gradient is 0 at that point. We're looking for a t value that we could isolate s. And by the looks of it, there's going to be 2. Can you spot where the other stationary point is? That's right, it's at q. So when we have q and s, we should get 2 results here. That's what I'm hoping for. If we multiply both sides by 2t, we end up getting 3t squared subtract 16t plus 16 equals 0. And this hopefully will have 2 solutions, right? That's what we're looking for. What have we got? Should be okay to do on top of our heads. we've got 4 and 4 for 16, and we've got a 3 interaction. So 3t and t for sure. And definitely both 4 because of the 16. And, well, it has to be positive, so we're going to be looking at that. Fluency, hey. Now, the two values of t that we've got are 4 for the bracket on the right, and we do a little rearrangement. We move the 4 over to the other side. It becomes positive and divide by 3. Which one is which? I guess that's the question. We've got two points for t. And the thing is, like, t doesn't really relate to the Cartesian equation, right? So you've got a t that is both positive, and you'd expect one is positive, one's negative to sort of help you out. But it's easy if you just put the t value into the x equation, right? So this is the equation that governs it. If we put in 4 is the easiest one to start with, we get 16 take away 9, that's 7. I remember doing that earlier. Okay, that's q. So this refers to point q, and this one here refers to the one that we're after, which is s. So that's really good. We've got a t value for it. And all we need to do now is put the values of t into the two equations that we have. So let's keep them in sight. Where's my mouse? There you go. There, no, not mouse, my pen. Where are we at? So x equals 4 over 3 squared, take away 9. So the x coordinate at that point, we're going to have 16 over 9, take away 9, which that's going to be a negative, isn't it? So we have negative 65 over 9 for a common denominator. That is looking good because it's what we have in here. Same for the y. So we've got the y equal to, we're going to put 4 in. Wait, we're putting 4 over 3 in, sorry. We're going to put 4 over 3 in. Not the best thing to work out, but as Maths Explained was saying, I'm total agreement. Why bother not using your calculator, right? That is actually a bother. 4 take away 4/3, blah, 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 yada, yada. It does become 256 over 27. How do I know? I did check earlier, but there you go. So we've sort of proved that the coordinates are there. Whew. Okay, so not the quickest of questions because parametrics, you know, they are pretty difficult in some way, but they're also, this is a big question. It's 14 marks, so you should expect to use a decent amount. Now comes the region bounded. This is the integration question, the integration part that we've been looking for. And yeah, easy to slip up on this. Super easy to slip up because, you know, you've got different values for x and t. So we're going to talk through that. Can we just clear everything? Are we going to lose everything? I've got it written down at least up to this point. So I'm going to clear the drawings. Yes. Okay, let's start again for space. It's always nice to stay neat. All right, here we go. The region bounded by the curve x, sorry, the curve in the x-axis is shown in the figure above. Thankfully, it's all above the x-axis. Super useful, nothing clever needed exactly, but we need to determine the value, the exact value in that region. We're going to need some interesting points here. Q was where t equals 4. That was the last thing that we did. What was P, if I remember rightly? P was, what was P? P was where t was equal to 0, I think. Just gonna go with that. So t equals 0 for that one. So we've got a couple of t values there. And if we're talking about the curve, we could draw it again. Could be nice to have a separate diagram to draw on. Super smooth, like it. Very cool. And something like this. Okay, that'll do, that'll do. There's P and there's Q. T equals 0. Now, under this definition, we have an area that we're looking for. So we can say area is equal to the integral between the two t values. I mean, typically it's like the x values. If I was going to do normal integration, it'd be something like, I don't know, y function d of x. Maybe we could have y of x. So it'd be something like this. But in our case, we don't have that. We've got sort of t values. And so it doesn't make sense to do it this way. For a start, our y function is not in terms of x, it's in terms of t. And therefore, this shouldn't be dx, it should be dt. So we have, if you want, just like to remember that you have like the formula you can use, but I like to sort of derive it each time. I have a t value at the top. This is almost like integration by substitution, because you're replacing elements that were in terms of x with t. Yeah. Am I putting an emphasis on t? Because, like, I don't know, I have at the very start realized I'm using a lot of t here, which is my channel, of course. And then we have y of x, which actually, we actually have y of t. Okay? That's great and everything, but we want it in terms of t, not dx now. And the only real way to get around this is to say, well, if we put a dt there, we can cancel that dt out so long as on top we have the dx that we had before. So in fact, it's an equivalent function. How does this work? Well, it's actually chain rule. That's how we can get away with this. Chain rule is like super important. Like, you've got to understand chain rule before you do anything in calculus. Anything. It's everywhere. So here we go. We've got the dx by dt, which is very good for us because we can find that. We have a function of x in terms of t, and we've got a function of y in terms of t. So we can go ahead and actually use this straight up. And a bit of substitution is going to go in. I'm going to just abbreviate that, call it a. And we've got our t2, which is 4, and our t1, which is 0. And our y function, when expanded, was t cubed, subtract 8t squared, plus 16t. I'm going to use brackets now because things are getting a little bit complicated. But dx by dt was the derivative of the x part here. So don't really need to worry about what that was. I could do that on the top of my head on the go. Now everything looks in order in the world. This is what your function needs to be with respect to. And some people like to miss this part, but it's actually really important to be precise. And after this, it just becomes a game of expansion. So probably tidy it up before we get to this point. We're going to expand, like, that wasn't the best arrow because the pen came off the board. There we go, undo. I'm going to go the other way. The 2t is going to come in and multiply all of these terms. That's what's happening. And we're going to get 2t to the power of 4, therefore. Subtract 16t cubed plus 32t squared, still respect to t. I could probably get away with saying d. It sounds like t. And the area now is going to be when we put this lovely thing into... Wait, we've got to integrate it first. Don't you even get ahead of yourself. So when we integrate it, we're going to put it into these square brackets. Okay, so that's once integrated, that's when we put the stuff in. So we add 1 to the power. I often like to put the t first, add 1 to the power first, and then sort of multiply by the reciprocal of what this new index is. The reciprocal is 1/5, right? So I've got then 2/5 out the front. I kind of do it all in one. I don't know, it's just me. So I'll do it again here. T, that's going to go up, and it's going to become 5 there. Oh, it's not. What are you doing? What are you doing? Always double check. Also, keeping things in line is probably a reason that jogged me to actually double check this and think, hey, hold on. Always be double checking. And now if we're going to do this, we're going to divide by the 4. We're going to end up with 4 at the front. And it's going to stay negative. We've got the t. We're going to add 3 to that. Add 1 to that to become 3. And then we're going to multiply by the reciprocal, so 32 over 3. And we're putting the numbers 4 and 0 in. Straight away, good habits come around. I'm going to open 2 brackets like this, put a subtraction. Why do I use brackets? Because the amount of times that people get caught out with this negative here, this negative will apply to everything in the second bracket, right? It's not really a case here, but it's just a good habit. Why is it not a case? Because when this 0 goes in, like everything's going to disappear. But I like to keep those good habits, for better or for worse. Whoa, now you're asking 4 to the power of 5. Time for a calculator. Let's look at my previous working out to make things nice and quick. Don't want to be here mental arithmetic on camera. It would take forever. It's an interesting thing. If it's t to the 4 and t is 4, and then you're going to multiply it by 4, technically it's t to the 5, right? 1024. Promise you that is a 2. I know it looks a bit crippled. 1024 over 3. And that's all going to come down nicely in the calculator to 1024 over 15. And you've got your final answer. What was this all dependent on? Like, everything was breezy after this point, right? It's all dependent on understanding this definition, knowing that you have this and that you have this, and confidently exchanging the parts so that it's in terms of t. This is a very important principle that you'll see in integration by substitution. It's like the whole point of it, that you make some substitutions to make life easier. This didn't really make life easier, it just allowed us to cope, but you get the idea. Your teacher says don't put, you will lose a mark. Your teacher has high standards, I believe. And that's not a bad thing. If you want to always put the -0, at least it's here. I hope he's not saying that you put it there, because this is literally an answer at this point. But if here, I won't write it on. I think you can see where my cursor is. If here, then there's nothing wrong. That's actually showing that you know what happens to that point, right? So you're putting it in and you're saying, well, that turns to 0, so that's why I'm going to ignore it. If you just suddenly got rid of everything there and did it in your head, the examiner is going to be making assumptions about whether you really understood what was going on. There's a lot of examiners that will write, okay, he got the one, well, they, should we say, got the 1024. I'm just talking about myself, obviously, but if they got the 1024 over 15 and they were very careful to make that sure that looked like a 0, yes, because I'll mark them down otherwise, then, okay, I'm going to give them 4 marks. How many marks was that? 5 marks? Whatever. I'll give them 4 marks because they got to the final answer. There's a lot of examiners that do that. So don't worry too much. This is just a fantastic habit. Right, lingered on it too long, I think. There's the question complete. Let's have a look at another one. As long as we're not running out of time. We've really, there were a couple of issues, weren't there, with the stream, but let's just sort of get going. Here we go. We've got an integration by substitution question. Hopefully you can see that enough. And maybe we'll make this the last one because of time. But we have nothing in the 5th one. So what's going on? Maybe we will keep this the last one because that's a good range. I'll just quickly have a look what I had planned and see if that was a better one. No, it's just another substitution. That's fine. And question 5. No, I was only going to do 4 anyway. So I'll tell you what, we will leave it at this one. And we'll make this the last one. Because we've done the whole range now. We've done parametric, integration by parts, and then integration by substitution. And it's, I will challenge everyone to not just do this one, but to do the one that I posted in the Discord, in Maths Explained Discord. that I said could take you up to 2 weeks. My favorite question of all time. Absolutely brilliant in terms of what you're going to get out of it. And it's so rewarding. If you want a challenging one that is your level, go for it. Right, let's get started. One good thing about integration by substitution is the methodology is algorithmic, meaning you follow the same steps each time. You can't really go wrong too badly, but there are some tricks along the way to help us. Typically, and I don't know if Maths Explained does the same, but I always begin with the substitution because we're looking to replace all of the function of x elements and the dx. We're trying to replace them with a different letter, namely du, and namely f of u. No funny jokes. So in this setting, we want an expression for dx, which also includes du. So the first thing to do is to differentiate your substitution. That's like really bread and butter, first thing to do. We love e to the x. It stays the same, one of your standard derivatives. And the 1 disappears. Now we're looking to find an expression for dx so we can replace it. So we just do something which, did you know or not, is actually slightly, it's not illegal because that's like, it's not litigation. It's not technically a great thing to do, but we treat it like a fraction. So du, should we do it all in one? We'll swap the dx with the e to the x, and we end up with this. Why do I write it like a fraction? Technically, you could write du 1 over e to the x. You could even go as far as to do e to the minus x du. And these are a couple of rearrangements. There's nothing wrong with them. Maybe they suit what's going to happen. But I would always just write it as a fraction. It seems to be neater for me. So don't worry if you haven't done that. The e to the minus x is useful if in your original function you have an e to the minus x. That can actually be really cool to cancel stuff down. So now I've got dx on its own. I can make a substitution for dx in my question. So e to the 2x, subtract 2e to the x, all over e to the x plus 1. Now this is where we're going to be really super careful. Where we have the dx, what happens with this? I told you already it's slightly not allowed to do this, but this is what's going to happen. We technically, using this here, don't have a multiplication in between these two. It's like really easy to mistake and think that there's a multiplication there. It's actually a big separation. Technically, it's more like a multiplication at the front where we have 1 over e to the x, and then in between this function here in the du is a big old space. I like to exaggerate it because all this is telling us is now that it's with respect to u. And it's this function part that's going to go on and simplify the function for us. So let's do it. Let's see what effect this has. It's really cool that the e to the x is going to cancel. Hopefully, we've got a factor of e to the x on top, if you can see it. It's maybe slightly hard to see, but we could even combine it down the bottom there. Another thing to notice, actually, is where the substitution comes from, because I've just noticed, before we carry on, that the substitution was e to the x plus 1, and that is exactly what's on the denominator here. So I'm going to be cheeky and do a couple of things there. I'm going to say that u can be the denominator. We're going to replace that. And then we're going to have e to the x on the bottom. And on the top here, just as before, because I don't want to change too much all at once. Now that makes it a bit clearer that we're going to be factorizing this down. So the e to the x on the right is going to disappear. And here we're just going to be cancelling that down as well. So what we end up with is not e to 2x, or you can think about that as e to the x squared, right? So you've got e to the x squared would be e to the 2x, because you would multiply that. So just going to left with one of those rather than squared. Take away 2, and that's now cancelled that bottom one, so we just end up with u on the bottom. On our journey to replace everything that is to do with x, we have one last little thing. Now, you're told to get e to the x by any way possible. Typically, we're going to find it in the original substitution. So if we just get that out again, we've got e to the x plus 1. If we can isolate the e to the x, that would be really cool. So we could say u minus 1 equals e to the x. And we could replace that in there and find a jolly good expression. There is a couple of ways of doing it, but e to the minus 1 minus 2. I think here we could even say, all right, if that was minus 2, then we take away 2 from both sides, then we'd have u minus 3. You could do it at that end. It might be neater to do it that way. Bear with me while I write this again. We're going around the page on a giant chase to find the answer. Du. All right, so things are looking a lot more simple. Let's remind ourselves of where we started. Disgusting. But now we come down here and things are looking pretty beautiful. Things are looking no longer year 2. Things are looking more like year 1. And the final thing to do, I suppose, I think is best, to do some sort of simplification. We're going to divide both terms by u. So we end up with 1 minus, now this is going to be 3 over u, but it's probably best to leave it like that rather than make it 3u to the minus 1, because this is in a good form for integration. We call that the Lun form, I suppose, if you will, the form that we can use Lun with. If you know anything about integration, we got the basic numbers will just, they will add. I mean, I could do it like properly and say that we've got 1u to the power of 0. But with just any numbers, we're going to put a u next to them. The u, because now it's with respect to u. It's very easy to start putting x there because you've done x forever. So just be careful on that one. We know that 1 over u will integrate to be ln u. And this is a great time for me to bring up something that I wanted to bring up earlier. Please do not forget the method that allows you to really sometimes simplify what's going on. If we've got a factor, we call this an integrating factor, right? Let's be more precise with what we're writing here. This is a nice pink. This is with respect to u. If we have a factor that we can see, this is a numerical factor, okay, like a constant. This is called an integrating factor, and it can be taken out. So I'm just going to write to the left here, save space. The 3 can be taken out the front. And this is the same question. I encourage, if there is a factor, to take it out. It actually can sometimes make things so easy, especially if it's a negative. If there's a negative in there and you don't want to work with integrating negatives, take the factor out and do yourself a favor. So under the idea that this becomes 1 over u, then this is 3 multiplied by the result of the integral of 1 over u, which is ln u. Okay, so we're going to then be subtracting 3 ln u plus c. Don't worry about the modulus brackets. They're there for a technicality. They don't have any bearing on where we're going with this. The original question wasn't a definite integral. So really there's not much to do here except realize that the original question actually asked us to integrate this with respect to x. So if we're now going to give them the question like this, it's not really the answer. Okay, this is in terms of u. So all we have to do is remember what u was equal to with our substitution up here and plug that back in, which is e to the x plus 1. One matter that I need to clear up is that when we integrate this here, it's no longer that. So I'm just going to make that clear. So let it be known for the record, I knew that that was happening and I've double checked. So when we have the e to the x back in, we end up with where should we go for this? E to the x plus 1 subtract 3 ln e to the x plus 1. What do we want to do with that? I guess you could tidy stuff up. You could say this plus 1 here can be absorbed into the plus c. I don't know if you're aware of that, but it doesn't matter what c is. It could just like be whatever you take it to be. So it currently would be c plus 1, which is basically c anyway. So technically you could be writing e to the x minus 3 ln e to the x plus 1 plus c. That would probably be the best form if you wanted it nice and neat and simple. Okay. Ugh, long questions, right? So when you get to year 2, tough questions. So just be aware of how long they might take, and saving time becomes really precious. What do I want to... Yeah, I think I covered that. Oh, another thing, while we're on the topic of integration, we've normally got, let's say, a graph and we're integrating it like this. And we've got a value down here and a value there, which would be our limits. So we could just put in some arbitrary numbers, so call it 5 and -1. And usually the top number comes here, and we've got our function with respect to x. But what happens if we set up the equation when we're doing integration with substitution, and it turns out that the smaller number is on top, like this. And it kind of spooks you, and you're thinking, wait, is this normal? Have I done something wrong? I give you like, how do you change that around? I just wanted to sort of put in here, there's a little trick that you could do to make sure that these do go the right way around. If you want to switch these limits, this and this one, then all you have to do is take out a negative. So we can make the whole thing negative, and then this can be written in a way that's less spooky. And sometimes maybe that works the other way around. If you want to bring that negative in, or you want to add it to the front, just remember to switch the limits. Okay, that's me done.
Happens most likely with parametric equations.
Oh yes, because you have to change it around, right?
Nice.
Yes, indeed. So I think that that's a pretty good range of questions, actually, in the end. What do you think?
So what do we have? Do you mind if I flip through the pages?
Not at all. Not at all. We had...
So we had mine, which was just basic integration, and then looking at the area problems. And then you kind of went into integration by parts, integrating logs, or the natural log. Then parametric equations.
Which, by the way, included differentiation and integration of parametrics.
Yeah, so good for someone who's just learning the basics. They could maybe stick to the first few questions, and then for someone that's looking for more challenging problems, they could give the last 3 a go. Yeah, good mix.
Yeah, I think so. Good revision. I think A-Level have got all of their sort of revision, their mocks coming up in January. So I guess if you want to see more of these ones, we can definitely do them. We have a few people in the crowd asking for some lower level stuff, some A-levels. So we have to sort of give a fair, broad spectrum. But this is today A-level integration. Really super important topic because it makes up approximately 40% of the syllabus, I'd say. In the questions that you're going to look at, it's about 40% of the marks is to calculus. You've got like differentiation, integration, all that stuff. So it's really important to master that. And after that, the most important topic is probably trigonometry. That's going to be 25% of what you're going to see, even if you're integrating trigonometry or you're using it or solving it. It's a big deal. So I'd definitely focus on those two for for your strategy? What would you say, sir?
Trigonometry 25%, you think?
It's pretty high, only because we use it in integration and differentiation. What would you say? I'm only it's only like a thought. I feel like I'm using trig all the time. It comes up in a decent amount of topics. It's at least 2 chapters in the syllabus for year 2, and it makes its way into other little areas.
It's a core topic, but in terms of the marks in an exam, I don't know. I would say 25%. I'm not sure, but like they really mix them up.
It really depends, doesn't it? It's harder these days to actually tell.
Yeah, so you get what, like approximately 10 to 15 questions in the exam?
Yeah, it can vary. Yeah, but yeah.
But, you know, usually they're all on different stuff. The one thing you could say is there's almost always some kind of integration area problem, finding the area of some region.
Yeah.
So even though that won't be like 25% of the paper, it will almost always be there. So
because I also count integration in terms of differential equations, and when you look at the modern questions that we have in the exam, there's always that big worded question which asks you to form a differential equation, solve it, and then talk about it, and it's like a whole page of writing,
Yeah.
Disgusting. But taking a bit at a time, it's okay.
Yeah, it's like a core topic that you know that will be there. And the same with trig. Trig will almost always, yeah, I mean, you could say almost 99.99% of the time they'll have questions on trig.
What's this?
If anyone has any questions, by the way, they can pop them in the chat.
I'll tell you what always comes up with trig is the R-cos formulas, you know them? X like plus or minus. That's like every single year because it allows you to use a trig graph and then model it for like what's happening and look at transformations and maximum points and minimum points for scenarios. It's like every single year. Like if I was doing it, I would focus on mastering the R-cos trig
so
anyway.
They usually call that problem solving using trig or something like that.
Yeah.
A cosine theta plus B sine theta equals R sine X plus or minus alpha, where R is greater than. Oh, I forgot I can write on the page.
Yes, the compound angle formula. And it in putting it in a certain format, it's like really useful for modeling because you may have like cosine plus 4 sine, something like this, and that's really hard to actually draw it. But if you can whittle it down to something in just cosine, let's say, I don't know, 0.1 if we're in radians, like this is really easy to draw because it's just a cosine graph like this, and it's shifted slightly, but you can find the maximum point, which is just the value of R, and this is going to model a situation where you'd want the maximum or the minimum, and they always have that question at the end where they mess it up like this, like 3 cos plus 4 sine. I don't know, maybe we'll make that 2, and they just sort of give you this bigger function, and you've got to think about how it's been transformed in relation to the cosine, not the original one up here. So yeah, it's a super good question, and it's really useful doing.
Yeah. So you can have either sine or cosine, right?
Yeah, and that's actually, they'll tell you what they want, but you could put it in any single form.
So what usually determines which one you use?
Typically what they tell you to use. I mean, I could get a question up now, actually. What have we got? Double angle, we've got our addition. They call it our addition in some places. 2, 7. I've got a book here, so we'll just look at this.
So HA says integration in A-level further maths any different to A-level maths integration?
Actually not much different, except you're going to use different functions like this will probably blow your mind, but I will write it anyway. You do have the sine function, and the way you say this is sine, right? But we also in further maths have the shine function. So just to give you a quick idea of that, we have cosine, right, so you know how to spell, but we also have, well, let's write it as cos. We also, don't get carried away there, we also have cosine, which is spelled cosh, like this, right? So these functions are very similar. They're related to the cos and sine. They have their own set of identities. So we will be integrating, things like that, which actually are very similar to the others. So it's not massively different in terms of that. I'd say that's probably one of the biggest differences. Except maybe you'll be doing second order differential equations as well. So with A level, you're only going to have first order, but with further maths, you're going to have second order. And a quick look at what that is, it's something like we've got a dy by dx, maybe we'll put a 3 there, equals 2x squared plus 4. That's a first order differential equation because it has a dy by dx in it. And a second order differential equation has a d squared by dx squared plus 4 dy by dx equals 10, something like that. And so it's got a second derivative in there. So it's kind of an extension. There are certain methodologies around how to solve this, that would be different from previous. We've got, as I said already, the hyperbolics. That's slightly different. Arc sine, arc cosh, arc than. I didn't mention than, but there's another one. So you can have tangent, which is tan, and then you can have the than, which is different as well. What else are we thinking? Yeah, I think that's it really. You differentiate those, but they're quite fun. Oh, I suppose hyperbolics as well. So the arcs. So you'll learn things like oh god, let me think about what this is now. If we have arc shine, if I remember, to integrate this is something like. I can get the other way around. It's x squared minus OX. I think it's the plus one. So this is a squared plus x squared. So you'll learn lots of identities, I would say. If you've got a good memory, you'll like doing further maths when it gets to year 2, because there are lots of standard results like this to remember. But this is the pure math stuff. It's
in terms of the integration rules, I don't think you learn.
There's not much more, is there, to like what we've done already?
It's just what you are integrating changes. Maybe.
Oh, Maths Explained. I forgot. Let me go to a different page here. Something with my mouse and my screen are out of sync, so you have to bear with me. Let's go back to this page and delete the drawings. There's some function you can, if you remember what this is, you can say halfway through. that goes like this. Do you remember these?
I don't know what the function is.
This is polar coordinates, right? So when you normally have in A-level and GCSE a coordinate system based on X and Y, how do you get to a particular point in space? Well, you go across a certain amount of X and then you go up a certain amount of Y, and you could define this point as XY. But in polar form, we talk about a particular point in terms of how far away this direct distance is, which we call r, and the angle that it creates here. So it's a different way. So how would I get to that point? Well, it would be an angle which was, quite a bit bigger, which is this one here. Call it x. We usually do it in radians anyway, but it would be an angle starting from this particular, what we call the horizon, and then the distance, like how far away it is, like directly, and it will be measured in that form. And these are called, I guess the topic's polar coordinates, and you measure it based on angles and distances rather than x and y's. And then that has a whole different, I guess a whole different calculus comes out, because you want to find the area of this shape here. This is called a cardioid. So like we have these shapes which look like hearts, and it's kind of cool. Yeah, I think that's modulus argument form is the same as polar. Do I call it modulus argument form? Not necessarily. See, modulus argument. What's that? Modulus argument. How do we relate the two together? It's pretty early on in the course, and it's typically more to do with a way of writing complex numbers. I don't think it's like massively related at all. Trying to think, there might be a conversion formula for it actually, but the modulus argument form might be, let's say we've got I don't know, some sort of cosine theta plus I sine theta. This would be a general form for a number like this, right? For a complex number, and this would be like modulus argument form if the complex number z could be written like this. Now you know that this is some measure of x plus a multiple of the imaginary plane, which can be rewritten in modulus argument form, which seems like it's pretty similar, but like it's I'm talking about something quite fundamentally different in terms of how I get to a certain point. Like imaginary numbers are on some plane that we describe in this way, and polar coordinates are literally on the real plane. They're literally things we can measure. It's just a different way of explaining a coordinate and getting to a specific point. But the great thing is they sort of play out in these very strange shapes. And one of them, my favorite, being the cardioid, which obviously, as you know, if you do cardio, you're running and it helps your heart. And a cardioid is in the shape of a heart. It's probably something to do with the Latin derivative.
What is?
What does it stand? What is the I never studied Latin, so I don't know.
I didn't actually know they were called cardioids. So what defines a cardioid?
A cardioid is like a shape that is like a heart in a way.
Right.
So it's a lot harder to explain in a short space, but basically the function in terms of polar coordinates, has a particular form that gives you specific shapes. And in the basic form, we have petals. But then particular shapes will give you cardioids as particular constants in that form change. Without the basis, it's very hard to even go into it. But it's really fun once you know the rules, and you can start drawing these really interesting graphs. But for the point of what we're making here, someone was saying, do we see calculus again in here? Well, actually, yes. You'll see it in the polar coordinates, because you'll do calculus with polar coordinates. If I remember rightly, something like if you're finding a tangent, dx by d theta equals 0, dy by d theta equals 0. There's a couple of things to remember. And the curve is often written something like this, I don't know. R equals 1 plus sine theta. And it will be between a certain values of pi. What you'll find is that it kind of curves as it goes out. So it's very interesting, and I feel like I'm babbling a bit because I don't want to go into it like deep, but that's where you'll see calculus again.
Cool. Oh, I mentioned the Archimedean spiral in a recent video. I think you can plot that with polar as a polar function. Would that be the right way to say it?
Yeah. Polar coordinates can describe polar curves, polar equations. What else? Yeah, polar equations. They're like, Cartesians in a way.
It's just a different way of describing a function's, like, that would maybe be neater.
How do I turn off the notifications? That's annoying. Anyway, let's just hope it doesn't come up again. So basically, say again.
I was just saying it's a different way of describing functions that might be neater for certain functions. Like if you try to describe this, so let's just draw it.
Yeah, it's an increasing distance away. Yeah.
If you try to describe a spiral with, regular x, y, or as a regular function in terms of x and y, it looks quite horrible. But if you use polar coordinates, it's something really neat. It's just in terms of theta, basically.
Yes, I can tell you what that looks like. I'll go through a few. So in polar form, the r stands for the distance away from the 0 point. And so if we have that constant, I don't know, say equal to a, this would describe like a circle with a distance a there. So you'd start at the horizon, and every point that you're plotting, think of it as loci if you wish, every point that exists exactly a away from there in terms of its angle is going to be plotted. And we go through a full motion, and that's obviously a constant distance away. And then we could have a shape like what you're talking, where we have it dependent on the angle, it will increase, right? So you could define it as, I don't know, a range of motion that went through to 2 pi or something. And you would have what you have there. You would start at the very beginning where the angle would be like 0. So it would be right at the very start, because the angle on the horizon is 0. So it doesn't matter what A is. But as the angle increases, it seems to get like further and further away from that center point. And so you end up with a spiral like this. Yeah, so it's a pretty cool way of describing.
So how neat is that? Just r equals a theta.
Super nice.
But if you were to describe that in terms of x and y, I don't know what it would look like really.
Yeah. This is really annoying. I didn't account for this, but hey everyone to my life. I don't think anyone's here at this point, but the review will be there. So anyway, this is us chatting with ourselves. I enjoy it, and I guess it's a good time to leave it here. This is a big 2-hour stream, a little chat about what further maths is like, and maybe if anyone's made it this far, I don't know. What's the bonus? Here's a smile. There you go. Just for you. All right, we'll stop streaming. I'm really, really appreciative of everyone that's made it along. And we love talking about this stuff. And we'll see you in the next one, I guess.